Hello. Good evening everyone. Good evening. I hope the video and audio is clear for everyone. I hope the video and the audio is clear for the everyone. Good evening. Good evening. Good evening everyone. Good evening. Good evening Vaishnavi. Good evening Akshara. Good evening Subhana. Now I hope the voice and the video is clear. Good evening everyone. Good evening. Now today we are going to see the very interesting lecture of our chemistry, that is thermodynamics. Now the class duration may be the somewhat high. Let's see uh, up to which topic we may cover. Okay, right. Now if while when I was explaining the concepts, if you are not getting anything, you just give me the question mark, right? Done. Next. And when I was giving the questions, try to solve it by your own. Okay. Now whatever may be the questions I was going to ask you, try to do it by your own. And the calculation part will play a very crucial role in the thermodynamics, because this calculation part will be helpful for you to speed up your concept or in the calculation in your exam. Okay, done. Right. Now the chapter we are going to start, that is the thermodynamics. Thermodynamics. Now what is the definition of the thermodynamics? Means thermo means the heat and dynamics is the motion, that where the heat it will be flow. Clear? Now what are the main points, that main things we are going to deal in the thermodynamics? Means actually first, what are the objectives that we are going to see in the chemical thermodynamics? Means the first point we are going to see, or better I will write the definition of the thermodynamics. What is the definition of the thermodynamics? The study of flow of heat or any other type of energy, into or out of the system, during a physical or chemical transformation, is called thermodynamics. Now thermodynamics short form I was going to write in the TD. Okay, don't get confused. If I was writing the TD, what does it mean? Now TD indicates that it is a thermodynamics. Clear? Now next, here what are the primary objects that we are going to see in the thermodynamics? Means first the objectives we are going to see in the thermodynamics. Objectives in TD. What are the objectives that we are going to see in the TD? Clear? First, calculate the energy change. Calculate the energy changes during chemical reaction. During the chemical reaction, how much energy change it has happened, that we are going to see. Done. Next, here the very key point that we are going to deal in the TD, in the TD, in TD, gaseous or gases, we are going to deal or ideal gases or ideal gases. We know the ideal gases, right? What is the ideal gas formula? PV is equal to nRT. Done? Clear? Now, here before going to start the thermodynamics, the very important terms of the thermodynamics we are going to see. Now, these terms will play very crucial role in our entire thermodynamics. Clear? May I know what are the terms that we are going to use in our thermodynamics? May I know what are the terms that we are going to use in our thermodynamics? Terms used in TD. The terms used in TD. May I know what are the terms that we are going to use in our TD? Now, the first term that we are going to use in our thermodynamics is, first is system. Clear? Now, what is the meaning of the system surrounding and the body? Yes, good. Now, first is the system. What is the meaning of the system? Now, the portion, any portion of the universe, any portion of the universe which is under our observation, Clear? Now, what is the meaning of the system? Now, the system, it indicates that any portion of the universe. Let's suppose if we consider our earth. Clear? Now, earth is our universe. Let's suppose. Next, if the any portion which is under our observation, let's suppose if I was teaching in the one class. Now, that class is in our observation. Clear? Now, the class is under my observation, right? That class is my system. Okay? Now, other than the class, the entire part is known as a surrounding. Clear? Now, that system, my classroom, and rest of the classroom, that we call it as a surrounding. System plus surrounding, both are present in the universe, right? So, system plus surrounding, we call it as a universe. Clear? Now comes to the thermodynamic point of view. Now, how to define the system? Let's suppose I was taking the one gaseous reaction. Just now I was said that we are going to deal with the gases called ideal gas. Let's suppose this one container I was taking. In this container I was taking the one gas, right? Now this gas is undergoing some chemical reaction, right? Now this gas is our system. Okay, this gas is our system. Now, other than this, where this gas is undergoing this chemical reaction, other than the remaining place we call it as what? Surrounding. Clear? Now, this gas chemical reaction and other than that place, that we call it as a surrounding, and two combiningly we call it as what? Universe. Clear? Now, the next point, next we are going to see, that is a surrounding. Next we are going to see, that is a surrounding. What is the meaning of the surrounding? Now the remaining portion of the universe. Other than the system, the remaining portion which we are having in the universe, we call it as a clear surrounding. Now the system plus surrounding is equal to universe. This will play very crucial role. You have to remember this point. Done? Next, the key term we are going to use, that is a boundary. Now, here the boundary may be the real or imaginary Clear? Now the boundary, it may be the real or imaginary. Clear? The real or imaginary, the real or imaginary surface which separates the system and surrounding, which separates the system and surrounding, which separates the system and surrounding is called boundary, right? Now see, here let's suppose one fixed boundary we are having. Here this one chemical reaction it is undergoing. Done. Now this is our entire universe, let us say. Done. Now in this universe, now our system, it is undergoing some chemical reaction. Now the leftover part, this leftover part we call it as a surrounding. Now this is our system. Now this leftover part we call it as a surrounding. Now here you can see, here we are having this part we call it as a boundary. Now what I said, the boundary may be the real or imaginary, right? Real or imaginary boundary which separate the system and surrounding is known as a boundary. Clear? Now the boundaries, here we are having the two types of the boundary. Now in our thermodynamics we are having two types of the boundary. We are having two types of boundaries. Now what are the two types of the boundaries we are having? First one is a diathermic wall, we can say, a diathermic boundary we can say. Now what is the meaning of the diathermic wall? Clear? Now what is the meaning of the diathermic wall? Which allows the exchange of heat. Which allows the exchange of heat. We call it as a diathermic wall. Now the second type of the wall we are having, that is a adiabatic wall. What is the meaning of the adiabatic wall? Means which does not allow exchange of the heat. We call it as a adiabatic wall. Clear? Now next, the very key point that you have to remember in our thermodynamics is the very key point. If you remember this very key points, the question terminology they are asking, that it will become easy for you. Clear? To understand the question terminology. Now the points which I was going to explain now, if you remember this one, it will be very helpful to understand the question terminology. What is that point? No, NOTE, note. Now in TD, work to be done. Clear? In the TD, work to be done. So sir, what is the meaning of the work and why it has came? Actually in our thermodynamics, if I was using the term energy, that energy may be changes in the thermodynamics either through the work or either through the heat. Here in the thermodynamics, work to be done, there should be movable piston or container should not be rigid. If these points are clear, now whatever may be the work done questions they are asking you in the question terminology, it will play very crucial role to understand the terminology. Okay, now I will explain with the diagram. Now see, let's suppose if this container is fixed, clear, or this boundary is fixed. Now here our system, it is undergoing some chemical reactions here. Now can we move this container? Now these boundaries which we are, where the chemical reaction is going, now can we move this boundary? Can anyone? Can we move this boundary? Can we move this boundary? In the first case, can we move the boundary? My dear friend, the complete organic, I said complete organic in the sense it is first year as well as second year, from the GOC to biomolecules. Now here the container, in the first case the container is rigid. In the first case the container is rigid. Now here the work cannot be done. Here in the first case the container is rigid. What I said in the thermodynamics, work to be done, there should be a movable piston or the container should not be rigid. Here you can see this container is rigid, means it cannot be moved. This container cannot move. Here the container means here the volume is constant. Here the volume is constant. If the volume is constant, work done will be the zero. Clear? Now if in the first case container is fixed, the container is fixed means volume is zero. Now in the second case, you can see in the second case this piston, if you apply the higher pressure or higher force, now this piston it will move. Now if the gas, whatever may be the gas that we are having inside our system, or the gas which is having in the container, if suppose it is having the high pressure, it will move the piston. So here the volume is not constant. Here the volume is not constant. Right? This is the one key point you have to remember. If the rigid container they have given, the volume will be fixed. Okay, if the volume will be fixed means work will not be done. Now if the movable piston they have given, movable piston if they have given means now the volume will not be constant. If the volume will not be constant, what it will happen? Now the container it will change and the work will be done. Clear? Done. Okay, fine. Next. The depending upon the nature of the boundary, systems are of the three types. What? The depending upon the nature of the boundary, systems are of the three types. Now what are they? Can anyone say me? Depending upon the nature of the boundary, systems are of the three types. What are the three types of the boundary we are having? Depending upon the nature of the boundary, systems are of the three types. May I know what are that three types of the system? Depending upon the nature of boundary, depending upon the nature of boundary, system are of three types. Now may I know what are the three types of the system we are having? Types of system. Types of the system. May I know what are the system? Right. Good. The first one is a open system. First one is a open system. Now, clear? Now, what is the meaning of the open system? Here, in the open system, both the energy and matter, both the energy and the matter is exchanged between system and surrounding. Okay, between the system and the surrounding, both the what? Energy and the matter is exchanging. See, this is the one very key point I will explain you. if the term energy, if I was using in the thermodynamics, now that energy, it will be either it will be exchanged through the work or either it will be exchanged through the heat. Okay, this is also one key point you have to remember. Either the energy will be exchanged through the work or through the heat. Done? Now, sir, what is the general example? Can you give it for the open system? Okay, I will give. Listen. Here, let's suppose if we are heating the water. This is one vessel. Clear? Now, this vessel is open. Done? Now, here we are having some liquid. For this liquid, I was heating this liquid. Done? If I was heating this liquid, now from the surrounding, what it is happening? Heat is exchanging through the system. Heat is exchanging through the system. Done? Now what it will happen? This water vessel will be, this water, whichever it is there in the vessel or in the conical flask, that it will get heat. Now after getting the heat, what it will happen? It will convert it into the gas and it will be exchanged to the surround. See, from year to year it is the energy is exchanging. Now water level, matter is nothing but liquid is converting into the gas, right? Now the liquid is converting into the gas means now year to year energy is exchanging, year to year matter is exchanging. Means both the energy as well as the matter is exchanging between the system and surrounding. System and surrounding is known as a open system. Clear? Next. Now the second type of the system we are having, that is a closed system. Now the second type of the system we are having, that is a closed system. Now what is the meaning of the closed system? Clear? Here only energy is exchanged, only the energy is exchanged, but not the matter. Clear? Now what is the example? Now same example I will take, the same example, but I will close the container. Clear? Now which we have taken in the open vessel. Instead of taking the open vessel, now what I was taking? Now I was taking the closed vessel. Done? Now the same heat if I was giving to the system, now what it will happen? Year to year what it is exchanging? Heat it is exchanging. But this liquid get heat from the surrounding. After getting the heat, again it will be converted into the gas, but it is not having a chance to escape from the system. Why? This is closed. This is closed, right? That's the reason it is not having a chance to exchange. Only the energy can be exchanged, but not the matter. It's known as a closed system. Next one. The next type of the system we are having, that is a isolated system. That is a isolated system. Now, what is the meaning of the isolated system? In this isolated system, both the energy and matter, both the energy and the matter is not exchanged. Both the energy and the matter is not exchanged. Clear? There is no any perfect isolated system in our universe, but we can take it as a, for general understanding, we can take it as a general example we can take, that is which one? Conical flask. If you take the general example as a conical flask, now arbitrarily we can say, now in the conical flask, most of the cases at the certain time, if you add the water in the conical flask at a, now the surrounding temperature is 25, our room temperature is 25, let us assume. Now when you have added the 30 to 40 degrees Celsius of the water in the thermos flask, most of the time, not total day, but at least few hours, it will be with the same temperature which we have poured, but entirely it will not be there, right? So that's the reason there is no any perfect isolated system in our universe. Done? Here just we can take it as a arbitrarily we can say there is no any perfect isolated system in our universe, but general example we can say it as a general example you can say it as a thermos flask. Done? Now here general example to understand. Now same thing. Now this is a one vessel. Now it has been closed. Done. Now when it has been closed, now what I will do, I will make thermally insulated, which does not allow the heat to the system. Now if I make the thermally insulated to this one, from here to here, it will not allow the Q, or it will not allow the heat to enter into the system. Let's suppose if this liquid, it is having some energy, and if it is converted into the gas, but it is also not having a chance to escape from this one, because here the lid is closed. So in the isolated system, both the energy and the matter is not going to exchange between system and surrounding. Clear? This is a one key point you have to remember. Done. Now the next one we are going to see homogeneous system and the heterogeneous system. Now what is the meaning of the homogeneous system and what is the meaning of the heterogeneous system? Means homo means same phase. Now homogeneous system means now the system with the same phase. Now what is the meaning of the homogeneous? System with only one phase. System with only one phase. Example, PCl5 gas, if I was heating, now it will be converted into the PCl3 gas plus Cl2 gas. Now see, now whatever may be the at the reactant side and the product side, both are having the same phase, right? Clear? This we call it as a homogeneous phase or homogeneous system. Now heterogeneous means, what is the meaning of the heterogeneous? Can anyone? Heterogeneous system. Now heterogeneous system means, now the system with two or more phase. We call it as a heterogeneous system. Example, CaCO3 solid, if I was heated, now it will be converted into the CaO solid plus CO2 gas. Done. Now the next we are going to deal with the very important concept of our thermodynamics, that is a thermodynamic properties. That is thermodynamic properties. So what is the meaning of thermodynamic property means? What is the meaning of the thermodynamic property means? Now let's suppose the physical quantities whose define the system completely is called as a thermodynamic property. Clear? Here let's suppose I will take one closed container. Done. This is the one closed container I was taken. In this closed container we are having the gas. In this manner we are having the gas. Okay. Now this gas is our system, because I was seeing this chemical reaction of this gas, right? So this gas is our system. Then now this gas to chemically react this gas, some thermodynamic parameters I was to fix. What are the thermodynamic parameters I was to fix? First is the temperature. Clear? Let's suppose I was assuming for our system the temperature, one thermodynamic parameter. My dear friends, these are the thermodynamic parameters. It will be fixed. Now temperature, I mean like thermodynamic parameter means you have to consider that is a temperature, one is a pressure, one is a volume, and one is a number of moles. Okay. Now I was fixing the thermodynamic parameter like this. Arbitrarily I was fixing. Let's suppose I was taking this system temperature is 300 Kelvin. And the pressure I was taking the 1 atm. Done. And the volume of this container I was taking it as a 10 liter. And the number of moles also I was taking it as a 10 moles. Done. Now here let's suppose what I will do, this gas which is at the corner, let's suppose I was giving this gas number 1 and the gas number 2, arbitrarily I was giving this gas number 2. Now for our system, what is the meaning of the thermodynamic property? The physical quantities whose values define system completely is known as the thermodynamic property. For the thermodynamic property, if I want to do the reaction, let's suppose for this container, if I make it as a partition like this, for this container, what I will do, if I make it as a partition like this, in the same fixed container only, best example, just for your example, I will take it as your classroom. Now this is a board, now this is a classroom, right? Now this is a classroom with closed. Now the classroom has been closed. Now this is our blackboard. Clear? Now this is our benches. Done? Clear? Now in this our classroom, temperature is 300 Kelvin, pressure is 1 atm. Now volume is 10 liter of this room, our classroom volume is 10, and the number of moles of the gases that is present in our classroom is 10. Okay? Now what I will do, when I was made a partition for our class like this, means if I was divided our class, then what happens to the thermodynamic properties? What happens to the thermodynamic properties? We'll see. Here, let's suppose in our class we are having the gas molecules like this. Clear? Done? Now let's suppose this is a gas molecule 1. Now this is a gas molecule 2. Here in our classroom, before making the partition, all the gases are having the 1 atm pressure. If I made it as partition also, the gas particles which are present in our classroom will have the same pressure. Why? It will be present in the classroom itself. It is not having a chance to go outside, right? Because the volume of the container is fixed. Means here this container volume is fixed. If this container volume is fixed, means this gas is not having a chance to go out from the container. Done? So whatever may be the pressure in the container, it will be fixed. So the gas of the gas 1 and this gas 2 will have the same pressure. Okay? So pressure is not changing after doing the partition. Next, temperature. Before the temperature of this gas is 300 Kelvin. After doing the partition also, I was having the temperature of that gas is 300 Kelvin only. Pressure is 1 atm. Now for the gas 2, pressure is also 1 atm. But what it will be changed, because before the container volume is 10. After making the partition, see, half of the gas particles has been at the separate side and another gas particles are at the separate side, right? Here also, if I make the partition, half of the students will be one side and half of the students will be one side. Let's suppose before the classroom strength is 50. After I was making the partition, now if I was divided the classroom, then what it will happen? 25 will be one side and the 25 will be other side. In the same way, now the volume also, when I was divided or when I was made the partition, what it has happened? Volume has been half, right? Volume has become half, right? If the volume has become half, now the number of moles also will become half, because volume is directly proportional to the number of moles. If the volume, if it is became half, now number of moles also will become half according to the Avogadro's law. Done? Now, clear? Now, here based on this one, what are the property when we have making or when we are changing, what are the properties are changing? One, volume and the number of moles are changing, and the temperature and the pressure, it is not changing. So the thermodynamic properties also the same thing. Now the properties which is having the fixed value for the system, for our system, whatever may be the property which we are going to see, or whatever the physical property which we are going to see for our system, if it is having the fixed value, that properties we call it as an intensive property. If any property with the changing of the system, that property is also changing, that property we call it as an extensive property. Clear? I hope it is clear for everyone. Clear? Now the extensive property and the intensive property is clear, right? Now, here we are having the two types of the properties. That is, one is extensive property, one is intensive property. One is the thermodynamic properties are the thermodynamic. Okay, thermodynamic properties are two types. Good. One is extensive property and one is a intensive property. Clear? Now, what is the extensive property? Now, what is the meaning of intensive property? What is the extensive property and what is the intensive property? Now, what is the extensive property and what is the intensive property? Means extensive properties will change. What? Extensive property can be additive and the divisible in nature. These are the mass dependent properties. Mass dependent. These are the mass dependent. First point. And the second point, this can be additive and divisible in nature. This can be additive and the divisible in nature. Means extensive properties can be add or we can divide. Clear? Now, what is the meaning of the intensive property? What is the meaning of intensive property? Intensive properties are mass independent because this is having the fixed value. Just now I explained very clearly, right? Pressure, temperature, the same type, it's also having the fixed property and it will not depend upon the mass. Clear? Now, they are not additive and divisible in nature. They are not additive and divisible in nature. Clear? Now we'll see what are the examples for the extensive property and what are the examples for the intensive property. These examples will play very crucial role, my dear friends. You have to remember. Now, extensive property examples are, first one, see, first example is mass. Sir, how come the mass will comes under the extensive property? Means, let's suppose mass of 1 kg and mass of 2 kg. Both are same or different? Both are different. So, depending upon the mass, what will happen? Quantity of the 1 kg and the quantity of the 2 kg will be not fixed, right? Means 1 kg is having the different quantity, 2 kg is having the different quantity. So, it is depending upon the mass. Second, next one we are having the length. Length, you can see, length, this is having the different length and this is having the different length and this is having the different length. All are not having the same length, right? Clear? Length is also changing depending upon the mass. Clear? Next one, area. Area is also will not be same. Clear? One, if it is having the square, if you take this one, it is having the different area. Now, if you take this much, it is having the different area. Clear? Now, area is also not having the fixed value. Next one, volume. Volume is also not having the fixed value. How? Because if you take the 10 liter, it is having the different volume. If you take the 1 liter, if it is having the different volume. Means, if any property, if it is not at all fixed and it is changing, then that properties we call it as a which property? Extensive property. Next, number of moles. Number of moles. Number of moles also will comes under the extensive property. How the number of moles? 1 mole it is having the different quantity and the 2 moles it is having the different quantity. Clear? Next one we are having the some thermodynamic energies that which we are going to study in this lecture. Those are internal energy. These also will comes under the extensive property. Internal energy. Now this can be represented by the E or U. Next, internal energy, enthalpy H. Next, entropy S. Next, Gibbs free energy. G. Clear? Next, force. Next, observance. Clear? And heat capacity. This will play very crucial role. Many of the students, they will get confused here. Heat capacity and molar heat capacity, both are different. Clear? Now, next, specific resistance. Now, these are the some examples for the extensive property you have to remember. Done? Next, and the very one key note you have to remember, that it is note. What is the one key note that you have to remember? Means ratio of extensive property, ratio of extensive property by intensive property, ratio of extensive property by intensive property will give extensive property. This is the one key point you have to remember. Sir, what is the general example, sir? Okay, let's take the number of moles. Number of moles is equal to what? What the number of moles formula? Weight. Weight is mass. Mass by molecular weight. Now you see, molecular weight will comes under the intensive property. Sir, how come the molecular weight will comes under the intensive property, sir? Now I will explain. Listen. Mass is a extensive property. See, I will take the water. H2O I will take. Just general example, I will take it as a H2O. H2O, first of all, I was taking from the tap water. This is H2O from the tap. Now the next H2O I was taking from the bottle. Some bottle I was taking. Now one H2O I was taking from the river. Okay. Now another H2O I was taking from the sea. Okay. Water molecule, water I was taking from the sea, water I was taking from the river, water I was taking from the tap, water I was taking from the bottle. Now, different sources I was taking. Tap is different source, bottle is different source, river is different source, sea is different source. But in all the cases, H2O molecular weight is 18, right? If I was taking the water from the sea, will the molecular weight of the H2O will be changed? No. H2O molecular weight will be fixed. Now that's the reason I said, right, the any fixed properties will comes under the intensive property. Clear? Either different sources, either any of the different sources if I was taking, but H2O molecular weight is fixed. It is not at all changing. Different sources, molecular weight of the H2O is fixed, 18. Done? So the fixed property will comes under the intensive. See, the ratio of extensive by intensive will give you the extensive property. Number of moles will comes under the extensive property, right? Clear? And the next example. Next example I will give you. Now, let's suppose volume you get. Volume is equal to mass by density. Mass by density. Clear? Now, mass by density. Density is also intensive property. And mass is the extensive property. Clear? Now the ratio of extensive by intensive will give you the which one? Extensive property. Clear, sir? How come the density is giving the intensive property, sir? Now I will explain. Now listen. Now the example that we are going to see for the intensive property. Intensive property. Now in the intensive property, it is mass independent and the values are fixed. Clear? Now the one key point you have to remember for the intensive property is ratio of two extensive property. Ratio of two extensive property will give intensive. Will give intensive. Ratio of two extensive property will give you the intensive property. First example is density. Density is equal to mass by volume, right? Mass will comes under the extensive. volume will comes under the extensive. Ratio of 2 extensive will give you the density intensive, right? Now second one. Second one, pressure. If you take pressure is equal to force by area. Now the force will comes under the extensive and area will comes under the extensive. Ratio of 2 will give you the which one? Intensive property. Sir, how come the force will comes extensive property? Means, let's suppose if you take the one rifle if you take, okay, one rifle if you take, for this rifle, now whatever may be the bullet it is coming, and if you take the one AK-47 or AK-47 gun if you take, okay, now from this whatever may be the bullet, now the bullet which is coming from the rifle and the bullet which is coming from the AK-47 gun, both are having the same forces? No, forces is not fixed. It is having the different and it is having the different. Clear? That's the reason it is changing, right? Extensive property. Force is a extensive property. Now the area is also extensive property. Ratio of 2 extensive property will give you the intensive property. Clear? Done. Next some example we are having for the intensive property is a molecular weight. Just now we have seen molecular weight is fixed value. Next, boiling point will also comes under the which one? Intensive property. Why? Same example, H2O boiling point is 100 degrees Celsius, right? Whatever may be the source you may take, that what it will give? It will give you the boiling point of the water at 100 degrees Celsius only. Clear? And the melting point also fixed value. Melting point also is a one example for the which one? Melting point is also one example for the intensive property. Next, molar heat capacity. I will explain very clearly about this one, molar heat capacity and heat capacity. Molar heat capacity will also comes under the which one? Intensive property example only. Next, and the next example we are having specific heat capacity. Specific heat capacity. This will also comes under the intensive property only. And next, vapor pressure. This is also having the fixed value. Clear? And rate constant K. And universal gas constant R. Clear? And viscosity. Clear? And the refractive index. This all will comes under the which one? Intensive property examples. Done? Intensive property examples. Clear? Now I will write one question. Now you have to say me the answer for it. Now I will write the one question. You have to say me the answer for it. Now X is equal to extensive. Done? Y is equal to intensive. Now what is the value of X minus Y? Okay, X minus Y, you have to say me the value. Done? Right. First one, density. Now the second one, melting point. The third one, area. Fourth one, we are having specific resistance. Fifth one, we are having force. Sixth one, we are having enthalpy. Seventh one, we are having entropy. Clear? Now eighth one, we are having volume. Ninth one, we are having heat capacity. 10th we are having mass. 11th we are having length. Clear? And the 12th we are having Molar heat capacity. Molar heat capacity. And the 13th we are having rate universal gas constant R, and 14th we are having rate constant K. Now send me the answer. What is the value of x minus y? 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 Should I say, or are you trying? If you don't know, give me the x. I am ready to explain. If you don't know, give me the x. No, extensive minus intensive will give you the intensive. No, 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 no. I am saying that x is the extensive property, y is the intensive property. Okay, x is the extensive property, y is the intensive property. Now out of 14, how many are the extensive property, how many are the intensive property? Here what I am asking, in the among 14, how many are the extensive property? That extensive property, if let's suppose extensive property are 5, so x value is 5. Let's suppose intensive property values are let's suppose 9. So x minus y, how much it will? 5 minus 9, what it will give? Minus 4. Like that I was asking the question. Okay, got it? I hope it is clear. Shrita is saying minus 2. Minus 2. Now we will see. Okay. Now we'll see. Here density will comes under the intensity, right? So this is y. Melting point will comes under the intensive property. This is y. Area will comes under the extensive property x. Specific resistance will comes under the extensive property x. Force will comes under the extensive property x. Now enthalpy will comes under the extensive property x. Entropy will comes under the extensive property x. Volume will comes under the extensive property x. Now heat capacity will comes under the extensive property x. Mass will comes under the extensive property x. Length same, extensive. Molar heat capacity will comes under the intensive y. Universal gas constant value fixed y. Rate constant value fixed y. That is clear. Now how many y we are having? 1, 2, 3, 4, 5. So y is equal to 5, and the remaining all will be the which one? Remaining all will be the extensive property. Clear? Now the x will be 9. Now 9 minus 5, now x minus y will be equal to 4, not 2. Okay? It will be the 4. See, y is equal to 5, x is equal to 9. You have to be very careful with this one. This type of the questions only they will ask. You have to remember, answer is 4. Clear? The answer is 4. Now some issue has happened with the camera. Now I was turning off the camera. Okay. Now if you are having any doubts, you can ask. Now next. Right. Next we are going to see that is a state function. Next we are going to see that is state function. Now what is the meaning of the state function means? Now before going to start the state function, now we are going to see the state of the system. State of system. Now what is the meaning of the state of the system means? Here let's suppose with a general example I will say. Now this is our one system. Okay. This is our system. Now here if all the thermodynamic properties are fixed, then the system is said to be in the state. All the thermodynamic properties are, let's suppose temperature is equal to 300 Kelvin. Now all the thermodynamic properties I will fix. T is equal to 300 Kelvin. P is equal to 1 atm. Clear? Now V is equal to 10. Then N is equal to something 10. Now these are the some thermodynamic parameters I was fixed. Clear? Now by changing at least one thermodynamic parameter, either temperature, either pressure, either volume, clear? At least by changing the thermodynamic parameter, now the state of the system will be changed. Let's suppose this is our system. System is in state because we have fixed all the thermodynamic property. Let's suppose I will heat this one. Now when I was increasing this system, then what it will happen? Now it will attain some other state, right? Now it will be attained to the some other state. Clear? Now the T is equal to 600 Kelvin, let us assume. Now the pressure has been increased to the 10 atm, let us assume. Clear? Now the volume will be same and the number of moles will be the same. Clear? Here now see, by changing at least one thermodynamic parameter, now the state of the system has been from the 300 Kelvin to it reached to the 600 Kelvin, right? Clear? Now this we call it as a state of the system. Now this one starting it is there, right? This one we call it as a initial state. This one we call it as a initial state. Now here this one after changing one thermodynamic parameter reached here, right? This one we call it as a final state. This one we call it as a final state. This is initial state and this is a final state. Clear? Now next. This is known as the state of the system. Next. State function. No. State function. Now what is the meaning of the state function? Clear? Now the properties which depends upon the initial and final state only. See, state function means which depends upon initial and final state only, irrespective of or it will depend upon the initial and the final state only. Clear? Independent of how the final state is obtained. It is independent of the how the final state is obtained. It is independent. Clear? Done? This sorry. It is independent of the how the final. It is no. It is independent of the how the path followed will try better. It is independent of the how the path followed. Better it will be independent of the how the path followed. Clear? Now here what are the properties that we can see, or what are the properties which will comes under the state function? Means if any properties which we can measure, the properties which we can measure, that properties will comes under the state function. My dear friends, you can see, let's suppose this is our system. Done? For our system, whatever may be the properties we can measure, whatever may be the properties we can measure, those properties will comes under the state function. Let's suppose for our system, I can measure the temperature. Clear? With the thermometer, let us do. Now I can measure the volume of this container. Clear? I can measure the what number of moles of this gas particles which are there. Clear? I can measure the pressure of this, which one? Pressure of the system. Clear? I can measure the how much internal energy it is changing. Internal energy. I can measure the enthalpy. Clear? Now I can measure the entropy. Clear? I can measure the Gibbs free energy. Gibbs free energy. Clear? Now these are the examples for the which one? State function. Any properties which we can measure will comes under the state function. Any properties which we can measure will comes under the state function. These are the examples comes under the state function. Next path function. Next one we are having the path function. Now what is the meaning of the path function? Which depends upon the path only, irrespective of the initial state and the final state. Clear? Now the property which depends upon path independent of how the final state is obtained from initial state. Example for the path functions are work or heat. So work or heat will comes under the path function. Sir, how come, sir? Now listen. Here let's suppose this is our system. Okay, and for our system these walls are which one? Diathermic wall. What is the meaning of the diathermic wall? Which allows the exchange of the heat. Now these walls are the diathermic walls. Okay, here the some gas we are having in our container. This is our system. Done? Clear? Now here for our system, now what I was giving the heat to this system. When I was giving the heat to this system, what it will happen? These gas particles will be absorb that heat. This gas particle will be absorb that heat. When this gas particle, after absorbing that heat, I will stop the heating. Clear? Now when this gas particle has been absorbed that heat, what I will keep here? I will keep the ice here. I will keep the ice. When I kept the ice, now it will reach to the some final state, right? It will reach to the some final state. When this system has been reached to the final state, what happened to the ice? Ice will be melt, right? When it has reached to the final state, ice has become melt. Here initially I just kept the ice to our system like this. I kept the ice to the system. When I kept the ice to the system, when it has reached to the, this is initial state. This is the initial state. Now this is the final state. When it has reached to the final state, now the entire ice has become melt, right? Where the ice has become melt? In this path only, right? Reaching from the initial state to the final state only, in this path only, ice has been melted. How the ice has been melted? Whatever may be the heat has been absorbed by the gas, that heat it is giving to the ice to melt, right? Heat it is giving to this ice to melt. Whatever may be the gas, it has been absorbed that heat. That absorbed heat is releasing by our gas. When it is releasing, what happened to that ice? Ice, by absorbing the heat which it is coming from the system, and it is getting melted. And when it has reached to the final state, all the ice it has become melt. Means in this changing from the initial state to reaching to the final state, in this path only heat has been exchanged, right? You can see this gas particles is giving the heat in this path only, right? From the initial state to when it is reaching to the final state, it is exchanging the heat. See, when it is exchanging the heat, entire ice became melt. That is in this path only the heat and the work can be exchanged. I hope it is clear for everyone. I hope it is clear for everyone. Is it clear, or still you are having any confusion? Or should I explain once again? Is it clear, or should I explain once again? My dear friends, is it clear, or should I explain once again? Right. Okay, fine. Now, next. Next we are having the heat capacity. Now, just now we have seen that heat capacity will comes under the which one? Which property the heat capacity will comes? Extensive or intensive? For the which property the heat capacity will comes? Can anyone? No. Heat capacity will comes under the extensive property. Now, how the extensive property it will be comes? See, no, heat capacity will comes under the extensive, not intensive. Now, when the heat transferred, when the heat is transferred, when the heat is transferred to the system, when the heat is transferred to the system, it raises the temperature, it raises the temperature of the system, it raises the temperature of the system. The increased temperature is directly proportional to the quantity of the heat observed by the system. Quantity of the heat observed by the system. Clear? Now you see here, this whenever the heat is transferred to the system, Q is the heat that it is directly proportional to the change in temperature of the system. Change in temperature of the system. Clear? Q is directly proportional to the change in temperature of the system. Right? Now, if I was removed that proportionality constant, one new constant it has came, that is C, that we are saying it as a heat constant. So the C is equal to Q by delta T. Q by delta T. Now here the delta T is equal to final temperature minus initial temperature, right? T2 minus T1. T2 minus T1 indicates that final temperature minus initial temperature. Clear? Done. Next one. The next species, next one we are having, that is specific heat capacity. Specific heat capacity. Now what is the meaning of the specific heat capacity? Now it is defined the amount of heat required, to raise the temperature of 1 gram of substance through 1 degree. My dear friends, you have to be very careful, through 1 degree. Clear? Now here you have to be very careful. Now listen. Here, let's suppose I was taking the heat capacity will be depend upon the mass, but specific heat is fixed for the 1 gram, right? You can see here the 1 gram is fixed. Now what is the difference between the specific heat capacity and heat capacity? Let's suppose I will take the 100 gram of the one substance. 100 gram of the substance. This 100 gram of the substance, its heat capacity is 100 kilojoule. Clear? 100 kilojoule. Next, I will decrease the mass. Now, if I decrease the mass to 50 gram, for this 50 gram, the heat capacity I observed is, when I was decreased the mass, heat capacity will be changed. Clear? I was observed that kilojoule. Done? Now, 100 grams, the heat observed is a 100 kilojoule, arbitrarily I was giving. Okay? It is not the fixed, just to make you to understand, I was giving this one. 100 for the 100 gram, 100 kilojoules of the heat it has been observed. For the 50 gram, 50 kilojoules of the heat it has been observed. Now specific heat is saying, for if you take the 1 gram only, in this from the 100 gram, I will take 1 gram. Okay? In this 100 gram, I will take the 1 gram. Now, in this 50 gram, I will take the 1 gram. Now, for the 100 grams, if I require the 100 kilojoules of heat, means then from this 100 gram, only if I check it for the 1 gram, how much heat I require? I require only 10 kilojoules, right? Now, for the 50 gram, the heat capacity or heat I required is a 50. Now, for only 1 gram, I required how much? 10 kilojoule. Means, here, whatever may be the heat capacity of the substance, for that 1 gram, heat capacity is fixed. So, what I was saying, all the fixed properties will comes under the intensive property. So specific heat capacity will comes under the intensive property, not the extensive property. I hope it is clear. Done? I hope it is clear. I hope it is clear. No. The amount of heat required to raise the temperature of 1 gram of the substance through 1 degree. 1 gram is fixed, right? He is asking you to raise the temperature for 1 gram of the substance only. Not 100 gram, 20 gram, 1000 gram or not. Only for the 1 gram. For any substance, if you take the 1 gram for that heat is fixed. Clear? Now the specific heat capacity formula, S is equal to, specific heat is represented by the S. Heat capacity by the mass. Clear? Now the heat capacity formula is Q by delta T, right? Clear? That is the heat capacity. Now Q by M into delta T. Q by M into delta T. Right? Now Q is equal to M S delta T. M S delta T. Clear? Now this is a one important formula. It will play very crucial role. Done. This is a specific heat capacity formula. Done. Next. The next we are going to see some process that it will play very crucial role in the first law of thermodynamics. Now, that is thermodynamic process. Now thermodynamic process we are going to see. Now what are the thermodynamic process that we are going to see? Clear? In operation which can change the which we can change the state of the system, is called thermodynamic process. Here what are the thermodynamic process we are having? Means first one is a isothermal process. May I know in this isothermal process which is constant? Can anyone? In this isothermal process which is constant? In this isothermal process which is constant? The class until first law of thermodynamics completed, I will say. Until I finish the first law of thermodynamics, I will continue. I don't know the time, but first law of the thermodynamics I will finish with the n number of questions. Maybe it will take 8:30 or 9. Once if the first law of thermodynamics done, I will end the lecture. Now here you can see, in the isothermal process which is constant? Isothermal process, temperature is constant. Good, Janakiram, good. Isothermal process, temperature is constant. Done. Now the second process we are having, that it is isochoric process. Isochoric process which is constant? Isochoric process which is constant? The isochoric process which is constant? The isochoric process which is constant, can anyone? Good. Volume is constant. No. Now in the isobaric process, next one, third one, isobaric process which is constant? Isobaric process. And the fourth one, adiabatic process. Clear? Now in the isobaric pressure is constant. The pressure is constant. In the adiabatic, which is constant? Heat. Q is constant. Heat is constant. Done. Now these are the some process that we are going to see. The very key point that we are going to see is cyclic process. The next process we are going to see, that is a cyclic process. Now what is the meaning of the cyclic process, and what we are going to see in the cyclic process means, cyclic process. Here, what is the meaning of the cyclic process? Cyclic process, here after the n operations, the obtained state is exactly equal to the initial state, is known as the cyclic process. Means, let's suppose I will take the one graph to make you to understand the cyclic process. P versus V graph I will take. Okay, P versus V graph I will take. Now I was started from the A. Let's suppose this is the A. I was started from the A and I was reached to the B. Done. From the B I was reached to the C. Done. From the C I was reached to the D. Now from the D I was reached to the A. Clear? Now you can see I was started from the A, I was reached to the B. From the B I was reached to the C. From the C I was reached to the D. Clear? Again the D, from again I was reached to the A. Clear? Now the obtained initial state and the final state is same, right? Now let's suppose I want to calculate the change in pressure in this entire cycle. If I want to calculate the change in pressure in this entire cycle, let's suppose the change in pressure will be the P2 minus P1. Now I want to calculate the change in volume, V2 minus V1, right? See, let's suppose this is a 5 atm. Then I was started with the 5 atm and I was reached to the 5 atm. Now the change in pressure will be 0. Now see, let's suppose this is a 5 ml. Now I was started with the 5 ml. Now I was reached to the 5 ml. Clear? Now the change in volume will be 0. Means in the cyclic process, all the state function, because pressure will be the state function, volume will be the state function, temperature will be the state function. Clear? Now all the state function values will become 0. Clear? Now this is a very key point you have to remember in the cyclic process. Clear? In the after, what is the definition of the cyclic process? After the n operations, if the obtained state is exactly equal to initial state, is known as cyclic process. Done? Note, this is a very key point. In cyclic process, state function parameters are 0. State function parameters are 0. Clear? In the state function, in the cyclic process, the state function parameters will become 0. Clear? This is known as a cyclic process. The next very key point that we are going to study, that is a one reversible and irreversible. My dear friends, based on this one only, we are having the work done formulas. Reversible process and irreversible process. So what is the meaning of the reversible process and what is the meaning of the irreversible process? Very fastly and clearly I will explain. Now listen. Reversible process means it is a slow process. It is slow process. Now just I will take one movable piston I will take. This is a one movable piston. In this movable piston, here we are having the gas, right? Now this piston has been stopped here. Why? Because let's suppose this is a P external. Now from here we are having the P gas. Means the gas will also having the some pressure, right? Now this is a P gas. P gas. So P gas pressure and the P external gas pressure both has become equal. That's the reason piston has moved here. Now I want to change this volume. Let's suppose this volume V1 is a 10 ml initial. Now when I was dropped the one very small stone to this one, what happened to the piston? Piston volume will be very negligibly, it will be very negligible change we can see, right? Means I was adding the each and every drop or every process I was doing. One small drop of the stone when I was dropping, what it will happen? For every drop of the stone, I can see the change in volume in the system. Change in volume in the system. How come, sir? Now let's see. Here, just I will drop the one stone here. Initially, it is having the 10 ml. When I was added the stone to that one, now the change in volume I was observed that 9.999999 ml. Let's suppose I was observed. Means by the every process, the change in volume in the system I can see, right? Change in volume in the system I can see. Means I can say when the change in volume when I was seeing, means P external and the P gas is become equal. That's the reason only, right? Here the piston is stopping. Why the piston is stopping here? Due to the P external gas and the P internal gas is becoming same. When I was added the one stone, I was seen very negligible change. Means P external gas and the P gas is same. Means in the reversible process, P external gas will be equal to the P gas. This is the one key point you have to remember. That's it. Nothing more than you have to remember in the reversible process. Just you remember this one. Now, when it comes to the irreversible process, what is the meaning of the irreversible process? Irreversible process is nothing but very fast process. Clear? Very fast process means just a general example I will take you. Balloon. If you take the balloon, if it is having the full of air in this balloon. Now, when it is having the full of air in the balloon, if you heat it, what? Now, let's suppose this is a balloon. Now, balloon it is having the some air in this one. Okay? Now, when I was given a fire to this balloon, what it will happen? This balloon will become burst. Clear? Again, when this balloon has become the burst, how much volume it has been changed? From this balloon, how much volume it has been changed, I cannot see. It has happened very fraction of seconds. Within the fraction of seconds it has happened. How much volume it has been changed? When this balloon, when I was given the fire to this one, balloon will be within the fraction of seconds it will be burst. So how much volume it has been changed, I cannot see. So that's the reason irreversible processes are the fast process and it cannot be reversed back. Now it is fast process. Done? Clear? Now here with the example of the gas I will explain to you. Now here let's suppose This is the piston. Now for this piston we are having the gas here. Done? Now here the P external gas, that it will be equal to the final gas. Now here it is a P gas pressure. What I will do, 10 kg of the mass, suddenly I will drop it. What it will happen? Now that gas piston will comes here and it will stop. Gas piston will comes here and it will be stopped. When the gas piston, when it has came and when it has stopped here, now how the system has been changed its volume? Now my question is, what I was saying, when I was dropped the 10 kg of mass to this one, what happened? If this P external pressure and P gas pressure, if it is having same, piston will not move. Why? Will the piston will move? No. When I was added or when I was dropped this 10 kg of mass to the system, this P external gas pressure is constant. This P external gas pressure, when it has become constant only, then only this when only this container has become compressed and it has been stopped here. Means I can see how much volume it has been changed. When either, let's suppose it is a 10 ml. When I was dropped the 10 kg of mass to this one, now it has reached to the 5 ml. Now the change in volume I can see only when the piston has been stopped. Means against the constant external pressure only our system has did the work. I hope it is clear. If the external pressure, if it is not constant, piston will not move. Why? If the P gas pressure and the external gas pressure, if it is constant, both the piston will not move. Suddenly when the piston, when it has absorbed, piston external pressure is constant. That's the reason only that gas has been compressed, and after it has become stopped. Why? Both the external gas pressure and the internal gas pressure became equal. Then until the external gas and the internal gas pressure, if it is not become equal, our system is used to change the volume. Means against the constant external pressure only the system has been changed. The which one? System has changed its or compressed or expansion, it has been done against the constant external pressure. Means the thing, very key point you have to remember for the reversible process and the irreversible process, only one thing you have to remember is, in the reversible process, P external gas will be equal to the P gas. Clear? In the irreversible process, if you remember this one, in the irreversible process, it will be happening against the constant external pressure. My dear friends, in your question, if you see the constant external pressure, blindly believe that it is a irreversible process, nothing to be changed. If the work has been done against the constant external pressure, if you have seen, work will be whatever may be the work, it has been done against the which one? Irreversible process only. Clear? Means here the final pressure means the constant external pressure, if it is happened, means now the P gas will be equal to the final pressure, that it is a P2 gas. P gas will be equal to the final pressure, that is called as a external pressure. P2 is nothing but P external pressure. Only these two key points if you remember. Now whatever may be the work done formulas we are going to derive, that there you will not get any confusion, or you will not get any you will not get any doubt or any confusion over there, and the question terminologies also it will be clear for you. Done? I hope it is clear, or still you are having any doubts? I hope it is clear for you, or you are having any doubts? I hope it is clear, or you are having any doubts? Should I move? Yes, right. My dear friends, now the almost 1.5 hours it has been done. Almost to complete the first law of thermodynamics and irreversible process questions and the reversible process questions, everything. Maybe the class may be end at 9. Okay. First only I was saying the class may be end at 9 because we have to do the questions and we have to clear the concept. Okay, right? Now be focused. Now I'm trying to explain you very clearly, because if I rush in the concept, you will not understand the terminology of the questions. So to understand the terminologies of the questions and to understand everything, I was explaining very clearly. Okay, done. The next very key point, that one very new terminology or one new thermodynamic parameters that we are going to study, that is the internal energy. Now what is the meaning of the internal energy? Can anyone? What is the meaning of the internal energy? Here the next one new thermodynamic parameter that we are going to study, that is a internal energy. My dear friends, then better can I do one thing? Now it is 7, right? Can I take the break? I will end the lecture here. I will take the break for half an hour and I will start the class at 7:30. Is it okay? Is it okay? Better you will also have some break. Instead of teaching continuously, 7:30 will start again. 7:30 to 9 will start. 7:30 to 9 will start. Okay? Is it okay? Okay, fine. Now I was ending the lecture here. I will start the lecture again at 7:30. Okay? We will meet you at 7:30. Bye. Okay.